Okay, so here's the second example in the notes. We have a system that has bar BA that's made of steel with a cross-sectional area given and a yield strength given. Member BC is a pair, so that means there's two of these aluminum bars having combined cross-section, so that's both the areas together, with a yield strength of 40 KSI. A factor of safety of 1.5 with respect to yield is required for both members. Determine the maximum allowable load P that we can apply to the structure. Report factor of safety for both members at the allowable load. Okay, so this is going to be kind of a multi-step problem. We are either going to fail with the aluminum bars first, or we are going to fail with the steel bars first. So we have to go back and calculate how much of this load P is being carried by BC and how much is being carried by BA. And then based on material properties, which one has the smaller load P that can be applied, because that's where we would have yielding first. So we've done several of these kind of work backwards problems. If you need help doing that, there should be still the video in statics review that's working through the cable system backwards, okay? So we want to find P, and we are going to have to assume failure of AB and assume then failure of BC, and then we're going to have to pick smaller P, because we don't know, because they're different materials and they have different areas and they have different modulus and they have different yield stress. We don't know which one is going to end up being limiting. Okay, so let's look at our aluminum and get our properties. Aluminum, we actually have two bars. They have a combined area of 4.50 inch squared. They have a yield stress of 40 KSI. So our failure is based on yielding for this problem, not failure with fracture, but we leave the elastic region, and that's where we're looking at the failure this time. Okay, I can also come over here with my steel, and the given area is 1.75 inches squared. It has a yield stress of 50 KSI and a factor of safety of 1.5. Okay, so we're going to have to start with equilibrium, because we have to figure out how much of this load P is being carried by each member. And we can look at this and see that it's a right triangle. So we know that BC, as the hypotenuse of the triangle, is going to carry a larger than 1 value of P, whereas AB is going to carry a smaller value. But because of the area differences and the material behavior differences, just because BC is carrying like a higher amount of P doesn't mean that that's necessarily where we're going to have yielding, because this area is so much larger than the steel area. So we're going to draw a free body diagram. We have our unknown force P. We have the force in BC, the force in BA, and this is at 55 degrees. So this is where statics comes into play. And we're going to start with summing forces in the y direction. And we have negative P plus FBC sine 55 equals 0. So P equals FBC sine 55. I also know that we're going to have to be able to substitute into our X BA in terms of BC. So I'm going to rewrite this as FBC equals P divided by sine 55. So this is what we're going to need in order to find out what load P is. And this is what we're going to need in order to do our algebra. So now let's sum forces in the X direction. Okay. And I'm going to have a negative BA plus FBC cosine 55, and all of that equals 0. So FBA equals FBC cosine 55. And now to get BA in terms of P, we can just substitute this in. P over sine of 55 times cosine 55. And we can rewrite it in terms of P as well. So we already have that equation set up when we have to back calculate. So P would be FBA sine 55 over cosine 55. And if you like math, that's just tangent of 55. Okay, so we have that done. So now, in order to figure out, well, which one is going to be the limiting factor, I know that P is in terms of the force in BC. And I also know for this aluminum members, I've been given area and yield. So I need to remember that stress equals P over A. And for each of these members, I know the stress and I know the area. So based on that allowable, or that yield stress with the factors of safety, I can go back and calculate the load P. So let's look at the steel bar. Let's just consider the steel bar limits. And I know that stress is P over A. And really that's going to be the force in AB over the area of AB. And I know that this allowable yield that we can use is going to be 40 KSI over 1.5 because we're reducing it with our factor of safety. And I just, for some reason, decided to pull. We're working with steel. So I can divide 50 by 1.5. I'm going to get 33.33. Okay, and now that's the stress that I can work with when I'm trying to figure out that load P that causes yielding. So I have 33.33 KSI equals force in AB divided by my cross-sectional area of 1.75 inches squared. So the force in AB that would exceed, okay, that would exceed what I'm allowed is 58.3 kips. Okay, so that's the force in the member AB. But how does that relate back to load P? Well, load P then equals FAB sine 55 over cosine, which is tangent 55. So I have 58.3 kips times tangent 55, and I get that force P that I could put on the system is 83.3 kips. So what this tells me is if I put 83.3 kips onto my system, okay, I will have failure, which, you know, it doesn't mean that the whole system falls apart. Again, it just means it's failing my criteria. I would have failure of member AB. So now what I need to do is go back and do the same thing for the aluminum bars. And I need to see, well, what value of load P causes failure. And again, it's not failure where we have fracture, but it's above the allowable stress criteria that we have in our design. Okay, so we're going to do the same thing. We can still see our free body diagram. We still have our equations, but this time we're going to assume that we have yielding. So we're going to have aluminum bars limit. And if the aluminum bars limit, then we're going to be working with the aluminum, okay, and how it's related with force P and the aluminum material properties. So again, I know that the allowable stress that I can have is going to be that yield divided by 1.5. So I have 40 KSI divided by 1.5. So the stress that I don't want to exceed is 26.67 KSI. And yes, that is a smaller value than the stress we got in the steel. But you have to remember that when we go back and look at stress equals force over area, we have to take into account the area of the bar. So stress of 26.67 equals force in BC. So what force in BC would cause the yielding when I'm looking at a 4.5 inches squared area, and the force in BC that would cause me to go above the limit that I set is 120 kips. Okay? So now I have to go back and look at, well, how is force P related to the force in the member? P equals force BC times sine of 55. So P equals 120 kips times sine of 55, and I get P needs to be less than or equal to 98.3 kip. Okay? So if I have P of equal to 98.3 kip, that's when I've exceeded the capacity of the aluminum based on my criteria. If I have P less than or equal to 83.3 kips, this would exceed capacity of steel when I'm looking with my criteria. So I have to choose the limiting one, because if I go above 83.3, then I have failure. So the largest load that I can have in this system is 83.3 kips. Okay, so now it says, tell us what the factor of safety is. Well, I know that if I'm using 83.3, then with my steel, I have a factor of safety of 1.5, because this is the one that ended up limiting using that factor of safety. But when I'm looking at the aluminum, okay, it's actually safer than the 1.5 I used to get this value of 98.3, because I'm only going to be loading to 83.3. So it's actually going to end up with a higher factor of safety. So let's look at the aluminum. So how do we get factor of safety? Well, first I have to go back and stress equals P over A, okay? And then this stress equals stress over factor of safety. And this is 40 KSI over, we don't know the factor of safety. But what we are going to figure out is what stress are we actually using. So stress equals FBC, but this is now based on P equaling 83.3 kips divided by the area of BC. So we have to figure out what the force is in BC, because it's not going to be the force that causes failure according to our criteria. We're using less. So I can go back to my equilibrium equations, okay? And the force BC is related to the force P by dividing by sine 55. Okay, so force BC equals P over sine 55. And we're using 83.3 kips divided by sine 55. Okay, and that is going to give us 101.69 kips. So that's the actual force that's in that member. Okay, we said we could have 120 kips if yielding took place first in the aluminum, but because yielding is being limited by the steel, we actually only have 102 kips. Okay, so now our stress is force over area, so I have 101.69 kips, divided by 4.5 inches squared, which gives me 22.6 KSI. And now I can continue here. So I have 22.6 KSI is the actual stress in the system. And that is going to equal what I'm allowed divided by the factor of safety. So I can cross multiply and I get a factor of safety of 1.77, which I guessed it would be larger. Okay, and it is larger. And the reason again that it's larger is because if we had failure in aluminum based on a 1.5 factor of safety, we could have 120 kips of force in that bar. And that 120 kips force in that bar would come from a load of P of 98.3 kips. Because we were limited in the system by failure in the steel, we actually applied a much smaller load, okay, to our system. And because we applied a smaller load to our system, we ended up with a smaller internal force. Okay, we had a smaller internal force. Because we had a smaller internal force, we had a smaller stress that would be in our system. Because we were going to be allowed 26.67 in the aluminum based on the material property and our factor of safety. But again, we had to use a smaller value. So we have a smaller stress. Because we now have a smaller stress associated with that 40 KSI of yielding, we end up with a larger factor of safety.